Hi, in this video we are going to talk about how to remove or delete an item or a node from an AVL tree. Basically, we have already discussing how to remove a node from a binary search tree. Basically, it is going to be exactly the same, but after every remove operation, we have to check whether we have violated the AVL properties or not. So basically, we have to check whether the given tree is a balanced tree or not. If it's not a balanced tree, of course we have to make some rotations to make it balance. If it is a balanced tree, of course we just have to return. So we have been discussing soft delete. We just have to mark a node to be deleted. It is not that efficient, so let's consider the next possibilities. Basically, we have three cases. The node we want to get rid of is a leaf node. Okay, we just have to set it to null. The node we want to get rid of has a single child. Okay, we just have to manipulate the references. But the most complex part is the case 3 when the given node has 2 children. Okay, let's consider all of them. The first is that we want to get rid of a leaf node. It's very simple, we just have to remove it. So for example, we want to remove node 5. We start at the root node, 5 is smaller than 12, so we go to the left. 5 is greater than 4, so we go to the right. So it's very important that if we want to get rid of a node, of course first we have to find it. So this is how we find a given node we want to get rid of. We check whether, okay, is it a leaf node? How are we able to decide whether it is a leaf node or not? If all of its children, so the left child and the right child, is equal to a null, it means that this is a leaf node. We just have to set it to null. Okay. The complexity is logarithmic as we have discussed for binary search trees. The second case is that we want to get rid of a node that has a single child. We just have to update the references. So for example, we want to get rid of 1. Okay, start at the root node. 1 is smaller than 12, so we go to the left. 1 is smaller than 4, so we go to the left. And basically, we have found the item we would like to get rid of. So we just have to set it to null, and it's very important that we have to tell the parent of this 1, which is the node 4, that pointing to the child of the node 1. So that's why we update the references like this. So the 4 is going to point to directly to the node -2. Okay, and we set this node 1 to be equal to a null to avoid obsolete references. Okay, of course the time complexity is logarithmic, this is why we like tree-like structures. What about the last case? We want to get rid of a node that has 2 children. Okay, basically we have already considered these cases when we were talking about binary search trees, so it is absolutely the same. Okay, we would like to get rid of 32. We start at the root node. Okay, this is the node we want to get rid of. It has a left subtree and a right subtree, so it has 2 children. Basically, we have 2 options. We look for the largest item in the left subtree or the smallest item in the right subtree. The greatest item in the left subtree is called the predecessor, and the smallest item in the right subtree is called the successor. Basically, we can choose. I usually implement a delete operation with the predecessor. So we find the greatest item in the left subtree and we swap it with the node we want to get rid of. In this case, we choose the predecessor, so the 23, and it's going to be the root node, so we just swap them. Why is it good? Because as you can see now, the 32, so the node we want to get rid of, is a leaf node, and we know how to deal with a leaf node. We just have to set it to null. Okay, so basically this is exactly the same as we have discussed for binary search trees. Okay, we can do it with the help of the successor. As you can see, after the swap operation, we end up with a situation we have already considered. It's going to be a node that has a single right child. We just have to update the references accordingly. Okay, the time complexity is logarithmic, of course. So the conclusion is that, okay, it is basically the same we have seen for simple binary search tree node deletion. But it's very, very important that there is a problem. When we remove a node from the AVL tree, then it may get unbalanced because of that given node is no more in the tree-like structure. Let's consider this situation. We have the root node 55 and we would like to get rid of 79. Before the remove operation, as you can see, this tree, this AVL tree is balanced. Okay, we don't have to make any rotations. It is a balanced binary search tree. Okay, we search for 79. It is greater than 55, so we go to the right. And we have find the item we would like to get rid of. It is a leaf node, we just have to set it to null. Okay, but let's consider this situation. It is unbalanced AVL tree, so the AVL properties are violated. We have to make a single right rotation on the root node. And with the help of the rotation, it's going to be balanced. So we come to the conclusion that, okay, we have to do exactly the same as we have seen for the binary search tree deletion operation. We just have to consider whether it is a leaf node, it is a node with a single child, or it is a node with 2 children. We have to do exactly the same, but after every deletion operation, we have to check whether we have violated the AVL properties. And what do we have to do if we have violated the AVL properties? We have to make some rotations. It's going to be exactly the same as we have seen for the insert operation. We just insert the node and we check whether, okay, is it a valid AVL tree? If not, we have to make rotations. So this is what we are going to do exactly, and we are going to implement it in the next video. Thanks for watching.